We have now convinced ourselves that if a system of linear equation x equal to b can be solved using Gaussian elimination, this system may also be solved using LU decomposition. However, we still don't have the idea how we are going to get the L and U matrices corresponding to an A matrix. Of course, we have seen in our last lecture that the L and U matrices may be obtained from Gaussian elimination. But then the procedure is not very efficient. Here we will present one method, that is Doolittle method, and it has a counterpart, that is Kraut method. Both are very similar. In these methods we find L and U matrices without using elimination. What we do here is that we assume the elements of L and U, we multiply them, and then we equate with the elements of A, and then under certain assumptions such as the diagonal element of lower triangular matrices are 1 or the diagonal element of upper triangular matrices are 1, under such assumptions it is easy to find L and U. Once we find L and U, we can solve the Ax equal to B problem using the two-step LU decomposition method. The advantage of this Kraut or Doolittle method is that we do not need any elimination during the evaluation of L and U. And we already know that when we are solving Ax equal to B using LU decomposition, we do not need any elimination since L and U are triangular. So overall, in this process that we will discuss right now, no elimination will be necessary. So let us see what we have. Let us take up a simple 3 equations, 3 unknowns system. Here I have 2x minus 3y plus 3z equals minus 2. Then 6y minus 8y plus 7z equals minus 3. Minus 2x plus 6y minus z equals 3. This is our Ax equals B system. Here the column vector B is minus 2, minus 3, 3, and the coefficient matrix A is 2, minus 3, 3, 6, minus 8, 7, minus 2, 6, 1. And our goal is to decompose A as a product of a lower triangular L and upper triangular U matrix. Now let us assume the elements of L are L11, L21, L22, L31, L32, L33, and since it is a lower triangular matrix, we know that there will be these 3 zeros above the diagonal. Similarly, the upper triangular U have 3 zeros below the diagonal, and the elements are U11, U12, U13, U22, U23, U33. If I now multiply these two matrices L and U, and then if I equate that LU with A, I can have one equation for each of the elements, which means that since A has total 9 elements, I can have at best 9 equations. But if we look at this L and U, I see that each of these matrices have 6 elements, so we have total 12 unknowns. It is not possible to find 12 unknowns just from 9 equations uniquely. So what we do is we can assume some of these elements, such as these diagonal elements of lower triangular matrices, to be 1. If we do so and then we try to solve this system, then we have 9 equations and 9 unknowns. Similarly, we can assume the diagonal elements of the upper triangular matrices to be 1. That will also give us 9 equations and 9 unknowns. And this method is called Kraut method, and the previous method where we are assuming L11, L22, L33 equals 1, that is something called Doolittle method. Both the methods, as you can see, are very similar. The differences between them are quite subtle, and we will not get into all those details now. We will see how we can find all the elements of L and U using Doolittle method. So we start with our usual equation and the L and U what we have just described. We know that the A is a product of L and U, and in Doolittle method L11, L22 and L33 are taken to be 1. So now we want to directly multiply this L and U. If we do so, this would be the product, L and U product. On the top you can see that U11, U12, U13 is there, and then we have additional 2 rows here. In these rows, of course, we have several cross term, unlike the first row. If I now equate A matrix with this LU matrix, and we can equate term by term, I should be able to get all the elements of L and U, since we have only 9 unknowns and 9 equations. So let us first write the equations. From the top row we have this U11, U12, U13 will be equal to 2, minus 3 and 3 respectively. This is very easy. Then the second row we again equate this L21, U11 equals 6, L21, U12 plus U22 equals minus 8, etc. Similarly, from the bottom row we have L31, U11 equals minus 2, and then the remaining 2 terms. First one equals minus 6, second and the last term equals minus 1. So now we have set 9 equations, and we have total 9 unknowns, 3 unknowns from the L matrix and 6 unknowns from the U matrix. So we should be able to solve all of them. The idea is to solve in an order that always in every equation we solve we will have only one unknown, and how you are going to accomplish that we'll see. But the basic framework is that we have to go either column by column or row by row, whatever way, but we have to go serially and not randomly. If we do so, we should be all right. Okay, now we'll follow the right sequence. Here you see that first I have this U11, U12 and U13. We get their values directly. Now I come to in column 1, row 2, so that means in this element, and from this element L21 multiplied by U11 equals 6, I get L21. Then I can come to the next element L21, U12 plus U22. You can now see that L21 is known from here, U12 is known, so I can calculate U12. Now I can come to L21, U13 multiplied by U23. You can see that L21 is known already, U13 is also known, so I can calculate U13. Similarly, I can go in L31, U11 equals minus 2. U11 is already known, so I can go for U31. Then I go to the next element in the same way. You can see here only the L32 is unknown, so I find L32, and then the last element here only the U33 is unknown, so I can find the U33. So you can go either use the first row is anyway super simple. There is no problem here in the first row, U11, U12 and U13, and then you come to the column 1, row 2. Once you have column 1, row 2, you can decide which way you want to go. You want to go row wise or you want to go column wise. Both are possible. If you go column wise, then you use U11, that known value, and you find L21, then L31 from here. Then you come to the row 2, column 2, and find U22 from here. Then you come down and you take L31 from here. Then once again you go to row 2, column 3, and you find out U23 from here, and finally you come down and get U33 from here. So you can decide you want to go row wise or column wise. Both way it is possible, and you can see that whatever way you do this solution, you are solving this 9 unknowns without any elimination process, in a sense that every equation has only one unknown. Now that I have this A matrix and the corresponding L and U matrices, I can solve this Ax equal to B problem. This Ax equal to B I can now replace with Lux equal B, and then I write Lp equals B and Ux equals P. You recall that this is a two-step method, and we will see there's two-step methods now. The first step is to find P. How you are going to find P? We solve Lp equals B. Here the column vector B is known and L is a lower triangular matrix. So finding P is very simple. I am not showing the detail, but you can figure it out. My B vector is this one, -2, -3, 3, and L matrix is here, which is a lower triangular matrix. So you start from the top. First you find for the P vector, first you find the P1, that should be equal to -2. Then 3 times P1 plus P2 should be equal to -3. And from that you get the P2, and similarly you get P3. There is no elimination step involved here. So now that we have P, we go to the next step where Ux equals P. Since we know P already, we can find X from here. And once again, U is an upper triangular matrix, so there is no elimination necessary. We can directly find X. Going from the X3, which means Z here, from the third equation we take Z, from the second equation we take Y, and from the first equation we take X. This is very similar to the back substitution that you did in Gaussian elimination. What is the utility of LU decomposition? LU decomposition is very useful if you know the L and U decomposition of certain matrix A, and then you are solving Ax equal to B. Now for solution of Ax equal to B, there are several methods available, but each method has its own issues. If you are solving certain Ax equal to B problem for many different B's, again and again you are solving, you have same A, many B's, this sort of a situation happens quite a bit in applied mechanics, and some of this situation you will see later on. I'll show you example when we talk about solution of differential equations. You will have same coefficient matrix but many column vectors. In such a case, if you know the L and U of A, L and U of A, to find L or U of A, you have to do some work. But since you will solve for same A and different B, so Ax equal to many different B's, so you take your time and effort to find the L and U of B, L and U of A, and once you do that, you can solve this way, this Lp equals B and Ux equals P in this two-step method very easily. The overall process of finding L and U, and after you find L and U, to find X at the end, does not require any elimination, and this is the real advantage of LU decomposition. Now that you have learned how to find the L and U matrix and how to use those L and U matrices to solve for unknown x, please try some of these equations that is given here. Solve them using LU decomposition. You must have solved them before using Gaussian elimination. Now you can solve them using LU decomposition and you can compare your solution. They must be the same if you are doing it all right. That's all for this lecture. Thank you, and I'll see you in next class.